and the empty footprint. So we can represent list segments. The list segment from P to Q represents sigma if this, same as before. And now instead of saying P equals null, we just say P equals Q. All right? And so given this definition of list seg, which we could notate this way, we can write the separating conjunction and define the loop invariant. Yes?
I thought that double bang inserted the pure proposition into a separating logic proposition. So is there a particular need for the double and n?
Yeah, so the double bang inserts a pure proposition into separation logic. A pure proposition makes no claim about what's in memory. So it doesn't require the memory is empty, it doesn't require the memory is non-empty. And if we also want to require that the memory is empty, then we just write it as double bang P equals Q and emp. So this is the spatial part of this assertion, and this is the propositional part. Now, some people represent a separation logic in which whatever operator they use to inject a pure proposition into separation logic also implies emp. And if you do that, then you would put a star here. But of course, star emp is, well, emp is a unit for star, so you wouldn't even need to bother.
But given list segments, is it the case that that might not be empty?
This has to be empty. So when the list segment is empty, what you have is x equals t, and there are no cells in the list segment. Okay, so let me show you another approach to defining list segments, and it will use the separating implication. So at the top I show, well, the Q separating implication R, also called Q magic wand R, because it looks like a magic wand. And what Q magic wand R means is it represents something in memory that if you added another piece of memory to it that satisfies Q, the whole thing would satisfy R. So that's sort of the semantic meaning, but the logical way to think about it is using this adjunction rule that P entails Q wand R if and only if P star Q entails R. So that's the axiom for magic wand. And we can think of it as Q wand R is the data structure that if you added Q to it, you'd get R. So now we can represent the list segment from X to T, representing sigma 1, as this. It's the data structure that if you added the linked list T representing sigma 2 to it, you would get the entire linked list X representing sigma 1 append sigma 2. And this whole thing separates from that linked list T to the end. So this magic wand part represents exactly this part of the list from X to T. This represents from T to null, and this represents from Y to null. So we can write the loop invariant for list append using list segments defined in either style. Either you make a new inductive definition or a new fixed point, or you can do it this way. You don't need a new definition of some sort of structure. You just say, well, subtract away the rest of the list from the first part, and that just describes, well, subtract away the rest of the list from the whole list, and that just describes the first part. Now, this is a very special case. We would like to think that this list segment from X to T could be attached to any tail from T to the end, no matter how long and containing no matter what elements. So for that, we can use a universally quantified magic wand. We can say for all sigma 2, if T is a linked list representing sigma 2, then X is a linked list representing sigma 1 concatenate sigma 2. And this is sort of the general list segment, X to T. And if we're going to fiddle around and change this list segment imperatively, we can know that this list segment can still be attached to it in the logic. Let's talk about binary search trees. So, last week, in the Verified Functional Algorithms lecture, I showed you pure functional binary search trees. And I showed that if you look up what you inserted, you will find it efficiently, in part because of the search tree property, right? That the nodes in the left subtree of a given node have keys that are less than the key at that node, and so on. Well, here's an imperative binary search tree with an insert function. So we have a struct tree, which is unsurprising. It has a key, a value, a left subtree, and a right subtree. The insert function doesn't produce a new tree, at least not from the point of view of the caller. It's an imperative C program. It modifies the tree in place, which is, of course, the way you'll find it in any standard algorithms textbook. So it returns void. The caller has to give the caller can't just give insert a pointer to the tree, because the initial tree is empty. It's a null pointer. Right? So what we do is we make the caller give a pointer to a single word struct, or in this case, a pointer to struct, a pointer to pointer to struct tree, the tree box. That's the single box at the top of the picture there. And the contents of that is updated as necessary by the implementation of the abstract data type by the search tree. Okay, so what's the algorithm for imperative destructive insert into a binary search tree? We start with a pointer, P. P0 is a pointer to the tree box. So if we dereference the initial value of P right here, so the first iteration through the loop, let's say, we get Q, which is a pointer to the first tree node. If Q equals null, well, Q is not equal to null. So we fetch Q arrow key, which is 5. And we might have this picture after one iteration of the loop. Now P points at a field of a struct. That's what this does. P gets the address of the field Q arrow right. This is great fun in C programming. Other languages don't let you do this. The disadvantage of doing this is that it looks complicated. But the advantage of doing it is it's more general. It handles the case when the tree is empty. It doesn't need a sort of sentinel node. You don't need a special case for no nodes in the tree or last node. And you can see that initially P pointed at a tree box here that was that single word pointer to struct tree. Here it points at a tree box which happens to be embedded within a struct. So after one iteration we're at that point, and after 2 iterations we're at this point. Now, think about how we're going to represent this in separation logic. In the loop invariant, one of our separating conjuncts will be that P points to, P is a tree box that contains some tree. In this case, the tree is just this node with the 7 in it. We also have the original tree box, P naught. But P naught overlaps with this tree P, so we can't put a separating conjunction between them. We have to say, well, there's a separating conjunction of this tree star the subtraction of this tree from the original tree. And that subtraction is represented by a magic wand. And the same was true at this point, where P is the bigger tree starting at 9, and the magic wand represents the entire tree except for that part. And in the beginning, P and P naught are the same, so the magic wand will represent imp. It will be the subtraction of the entire tree from itself. Okay. So we represent it something like this, that there's a tree box at P representing some tree T, that's this, and then there's a magic wand. But it's not that we're subtracting this tree from the tree we have. We're going to subtract it from the tree that we will have by the time we finish the finish the loop. Question?
So is it like a hole in the data structure that's waiting for the rest of the answer?
Right, it's representing a data structure with a hole. Okay, but we're careful to put here, if we put here the original tree, not insert xv t0, but just t0, we could put t0 here and t0 here, or t here, but since in this representation of it I didn't write down a universal quantifier in front of the magic wand, I have to be careful to talk about the tree I intend to have at the end, not the tree I have right now. Another perfectly good way to do this would be to put a universal quantifier here and say, whatever insertion I choose to do later, the tree surrounded by the dotted line, that portion will be compatible with it. So really, the most straightforward way to do this is with the magic wand, but sometimes with the universal quantifier, but sometimes that's hard to think about. So here's a different way of thinking about the same thing. All right, so let's look again at search trees. Here's what we had last week in verified functional algorithms. We had a pure functional program that implements binary search trees. So it's got this inductive data type, and it's got this insert function, which is non-destructive, of course. It just returns a new tree. Then we could prove the properties of this pure functional program using, where is it? Here it is, using the definition of the search tree property, right? It's a predicate on pure functional search trees, and it says basically the keys to the left of this node's key are all bounded above by this key, and the keys in the subtree to the right are bounded below by k. And using that property, we could prove things about the abstraction relation between trees and finite maps. And in fact, in the other chapter of verified functional algorithms, we showed that trees implement finite maps, right? We had table, that's the module type of finite maps with the properties of, with a get function, a set function, and this theorem get set same. If you insert something and then look it up, you get it back. And this other theorem get set other. If you insert something and you look up something else, you get back what you would have got if you'd searched for the original thing. Okay, so the functional data structure implements the high-level mathematical abstraction. So in the previous lectures, I've been talking about the mathematics of your application domain. And in the examples I gave in those lectures, the mathematics of your application domain was pretty trivial. Well, this is not so hard either, but here's the mathematics of the application domain. It's search trees and the search tree property and the fact that they implement this mathematical abstraction of finite maps. Now let's talk about the verification of the C program. So here's tree, well, we start the C program. I've put it all in the same module here, in the same .v file. If you're doing this in an industrial scale engineering, you would make this more modular. But here's exactly the pure functional data structure from the Verified Functional Algorithms textbook. We're going to use it exactly as the functional model that's refined by the C program. Now what? Here's tree rep, which is how, in separation logic, we describe that the data structure is laid out in memory. And this is a fixed point over trees, T. And since trees are finite inductive structures, we can make fixed point functions over them. If the tree is the leaf, right, the empty tree, then P must be the null pointer, and we have the empty footprint. If it's this tree with left child A and right child B and key X, well, the key value has to be representable as a signed integer. It has to fit in V, I guess. Whatever binding we're putting in V has to fit legally in a pointer to void. And then we have two subtrees. So at address PA, we have the left subtree. At address PB, we have the right subtree. And we can see that at address PA, there's a representation of the pure functional tree A. And separated from that, at address tree PB, there's a representation of the pure functional tree B. And it's useful that these are separated. The fact that they're disjoint means that if we go and update in one subtree, the other subtree won't be affected. That's the thing you get from separation logic. And then finally, there's the node, which is a data at address P, that it's a struct tree that contains this for tuple, X, V, PA, PB. So, tree rep, quite straightforward. And then a tree box, remember, is just a single cell that points to a tree. So it's a tree box at address B still represents a tree, a pure functional tree, but just in a different way with one extra layer of indirection. And here is that extra layer of indirection. It's this single word data at, right, whose type is pointer to struct tree. That's its contents. It's at address B. The pointer it contains is P. And separate from that, we have the actual tree itself. So this tree box rep represents one of these entire data structures. Now, here is the separation logic specification of the insert function. Okay? The precondition says, at address B, we have a tree box rep representing T. Oh, and the parameters contain the values they're supposed to contain, and the key we're trying to insert is representable as a signed integer, and the value we're trying to bind it to is actually a pointer. But look, the precondition says at address B it represents the abstract mathematical tree T, and the postcondition says at address B it represents insert XVT. Now, think about list reverse. The precondition said something represents this list, sigma, and the postcondition said something represents this list, rev sigma. So in that case, we are proving that a C function implements a functional program. But destructively, you don't get your old value back. Here, it's exactly the same. We're saying that the C program, insert, implements the imperative, the destructive implementation of a functional program. You start with T, and you get back the functional program applied to T. Now, You don't have to do this.